any object moves with constant speed in a straight line, unless it's acted upon by an outside agent. That fundamental principle is called the law of inertia.
Today I'd like to tell you a little bit about Galileo. Why is it that we always call Italians of a certain period by their first names as if they were good friends of ours? You know, it's not only Galileo. There's Dante and Leonardo and Raphael. It's strange. In any case, today I would like to tell you about our good friend Galileo Galilei. Here is a picture of Galileo made from a woodcut that was made while he was still alive.
Two very important men were born in 1564. William Shakespeare in Stratford and Galileo Galilei in Pisa. As a youth, Galileo had first set out to study medicine at the University of Pisa. But he soon realized that medicine was not for him. When he found out that there was no professor of mathematics at the university, he dropped out of medical school. He taught himself mathematics, wrote a few papers, and began to build a scholarly reputation. And in the year 1589, with the help of a well-connected friend, he was appointed professor of mathematics. At the time, the university was dominated by Aristotelian scholars who saw little value in mathematics. Galileo considered his Aristotelian colleagues to be fools and immediately got into trouble by baiting and ridiculing them. It soon became obvious that when his 3-year contract was up in 1592, he wouldn't be reappointed. So, when a position was offered to him at the University of Padua, he accepted it without hesitation. At Padua, he lectured in Euclidean geometry, Ptolemaic astronomy, and Aristotelian mechanics. He conducted his noted research on falling bodies and inclined planes. And in the year 1610, Galileo pulled off perhaps the greatest academic sleight of hand of all time. A Dutch lens grinder named Hans Liphery had discovered a remarkable new device, the telescope. As soon as Galileo heard about it, he figured out how it must work, came up with his own design, and built a telescope of his own that magnified images by about 9 times. Then he called together the city fathers of Venice for a demonstration in the famous tower in St. Mark's Square. He told them, "Look at the horizon through this device. With it, a ship approaching the city can be seen 2 hours earlier than it could with the naked eye. For a maritime power like Venice, this device is absolutely essential." Galileo didn't claim that he invented the telescope, but he also didn't bother to point out that he hadn't. The city fathers were so impressed that they gave Galileo a lifetime position at a handsome salary. And within 2 months, models of Galileo's telescope were being sold by vendors on the streets of Venice as children's toys. Galileo had made himself financially secure for life by selling the city fathers a child's toy. But Galileo had much more important things in mind for the telescope. He built a number of larger, more powerful telescopes, including one that would magnify images about 30 times. Today, 2 of them are on display in the Museum of the History of Science in Florence. With these telescopes, Galileo looked at the sky and made some remarkable discoveries. The moons of Jupiter, which even today are called the Galilean satellites. Mountains on the moon, the phases of Venus, and spots on the face of the sun. Even now that we've walked on the surface of the moon, Galileo's sketches reveal that his views were amazingly accurate. In time, Galileo's astronomical discoveries, along with the ideas of Copernicus, would intellectually shatter the serenity of the heavens. To anyone who dared to look through Galileo's telescope, what they saw was the beginning of the end for the world views of Aristotle and Ptolemy, and the beginning of a great deal of trouble for Galileo Galilei. By the early 17th century, Europe had seen the Renaissance, the Protestant Reformation, and the Catholic Counter-Reformation. Sweeping changes had shaken every part of the medieval system: religion, art, literature, music, mathematics, and the sciences, especially astronomy. Before the Renaissance, Aristotelian mechanics and Ptolemy's design of the heavenly spheres were the order of the day. They were the logical, accepted, and unchallenged natural order of the universe. And so it was until a Polish monk looked upward and saw things differently. In opposition to the Ptolemaic view, Copernicus saw the Earth as just another planet circling the larger, grander sun. Within the Catholic Church, some saw the Copernican system as a threat. It seemed like the Protestant heresy itself to challenge the absolute authority of the Vatican. Nonetheless, it took the Church 75 years to make her displeasure fully known. And in the interim, the Church had to contend with the problem much closer to home than the sun. Catholics and Protestants were locked in a war for the very soul of Europe. Copernicus, like Martin Luther, challenged the Church's interpretation of Holy Scripture. But the Copernican system also seemed to defy elementary common sense. Heavy objects naturally fell toward the center of the Earth, because that was the center of the universe. If the Earth really is spinning and hurtling through space, why doesn't everything fly off? And if the Earth really is spinning, why should an object dropped from a tower land directly below? Why doesn't it land in the next city-state or at least some distance away? 300 years ago, those were logical, intelligent questions. And Galileo Galilei set out to find the answers. Galileo was, despite his independent nature, a very popular figure, generally respected and admired. And to the Church, his God-given intelligence made him a favorite son. No doubt Galileo enjoyed the attention. His hunger for fame was enormous. But his thirst for knowledge and for the truth was even greater. Early in his career, while a professor at Padua, Galileo did quite well for himself as an academic entrepreneur. Among other things, he tutored royal princelings in subjects such as magnetism and mathematics. But in the long run, his use of the telescope was much more important. His first book, The Starry Messenger, revealed his remarkable observations. The publication of The Starry Messenger elevated Galileo to a position of renown throughout Europe. Yet in certain circles, his discoveries were not altogether welcome. Through his telescope, Galileo had seen something unimagined, or at least unspoken, by the followers of Ptolemy. The moons of Jupiter seemed to prove that the Earth wasn't the center of all motion in the heavens. Did he have within his sights the proof that Copernicus had been correct? Contrary to both Aristotle and the doctrine of the Church, was the Earth merely another planet orbiting around the sun? If that were true, the question remained, why in the world doesn't everything spin off? Aristotle's ancient view was that all things, by their nature, have rightful homes to which they want to return. His ideas of absolute rest and absolute motion seem confirmed by common sense. And based on the common experiences of everyday life, how could anyone take the idea of the Earth's hurtling through space seriously? It was one thing for Galileo to criticize the prevailing Aristotelian point of view, but quite another to show how and why things worked within the Copernican system of planetary motion. But even before the invention of the telescope, Galileo had prepared himself to do exactly that. To lay the groundwork for his law of falling bodies, he had painstakingly observed and timed balls rolling along inclined planes. These experiments also led him to another profound idea that would come to be known as the law of inertia. Galileo realized that a ball, after rolling down one inclined plane, would roll up another until it regained its original height, no matter what the steepness of the second plane was. If the incline of the second plane was shallower, the ball would roll farther along, not stopping until it was as far above the horizontal as it had been at the start. The more nearly the second plane was horizontal, the farther the ball would roll, trying to regain its original height. Therefore, on a perfectly horizontal plane with a smooth surface, a ball would never come to rest. It would keep rolling forever. This was the crucial realization that Galileo needed to explain why everything, including his critics, could keep up with the spinning surface of the Earth. A body in horizontal motion tends to keep moving that way forever. But everything on the surface of the Earth is in horizontal motion at exactly the same speed as the surface of the Earth itself. There's not even any friction to affect a body's motion, because everything moves together. With this remarkable concept, Galileo overturned the ancient Aristotelian dogma that it's natural for all bodies to come to rest. Although Galileo's concept was brilliant, it wasn't entirely accurate. Still influenced by the Platonic ideal of circular motion, Galileo thought that a body in motion would continue forever, but only in the horizontal direction, not in a straight line, but round and round, following the surface of the Earth. A generation later, René Descartes straightened everything out, giving the law of inertia its final shape. Objects in motion don't tend, by themselves, to come to rest. They tend to continue as they are until something interferes. That fact's easier to see now than it was in Galileo's day. Today, few would disagree that the planet Earth hurtles around the sun. A sun that moves around one corner of a galaxy that moves alone in a cluster of galaxies, all streaking through the unimaginable vastness of the universe. How does the idea of rest fit into this grand scheme of things? It doesn't. Nothing in the universe comes to rest. Instead, anything and everything will continue to move as it is in a straight line at a constant speed until something interferes with it. That's the principle of inertia. And it's both as simple and as profound as any idea that's ever been pondered. Obviously, objects can seem to be at rest, but that's only because they're in the same state of motion as the viewer. Whether an object is at rest or in motion depends completely on viewpoint, on whether the observer's moving right along at the same speed. Absolute rest does not exist. Absolute motion does not exist. Even hurtling through space at an incredible speed, relative to the moon or the sun or the center of the galaxy, the natural tendency of any object is to retain whatever motion it has. In Galileo's day, that was a very difficult concept to accept. To an Aristotelian, the motion of a cart required and had a logical explanation. Unless something came along to push or pull it, it wouldn't move. Therefore, its natural state was that of rest. But to the modern observer, a vehicle in motion needs no explanation. This coasting object will keep moving until the brakes, or something else, brings it to a state of rest. But what about an object that's not just moving horizontally along with the surface of the Earth? What about a projectile launched into the air? Or a ball dropped from a tower? Shouldn't the spinning Earth leave the falling ball behind? Galileo said it shouldn't. He said the ball should continue to move horizontally with the Earth, even as it falls vertically toward its surface. In the Renaissance, this concept was as hard to grasp as quicksilver. So Galileo offered his contemporaries an analogy. He asked people to picture a ball falling from the mast of a moving ship. To a sailor on the deck, the mast is standing still. He wouldn't be surprised to see the ball fall straight down onto the deck at the foot of the mast. But anyone on shore would see the ship and, of course, the mast in motion. An Aristotelian observer would have no doubt at all about what should happen. The ball should fall directly toward the center of the Earth while the ship sails out from under it. That sailor on deck would see the ball hurtle toward the rear of the ship rather than fall to the foot of the mast. Though the experiment was probably never performed during Galileo's life, the results are precisely what he predicted. The ball falls straight down along the mast. The ball falls along the mast because both objects, ball and sailboat, share the same initial motion. If they don't share the same initial motion, then the result is just as the Aristotelians would have expected. But when dropped from the moving mast, the ball falls vertically while moving horizontally with the boat. Together, these motions form a curved path, a parabola. Galileo realized that these same principles would cause the motion of any projectile to follow a parabolic curve, whether at sea or on land. A ball dropped anywhere on the surface of the spinning Earth behaves the same. Here, sharing the horizontal motion of the planet, it falls straight downward and lands at the base of the tower. In these terms, Galileo saw and proved something new under the sun. In 1616, Galileo was summoned to Rome. He was told to neither hold nor defend this idea of the Earth moving around a stationary sun. Knowing that the Church officially objected to the Copernican system, he waited for the right moment to convince them of the error of their Aristotelian ways. In 1623, Galileo thought that the moment had arrived. His friend and protector, the brilliant Cardinal Maffeo Barberini, became Pope Urban VIII. To enhance his case, Galileo wrote a book, a dialogue in which characters debated the Aristotelian and Copernican systems. As an author, Galileo was a clever politician. The Aristotelian character argued skillfully and was declared the winner, a ploy which was to be Galileo's defense against teaching the Copernican view. However, as any reader could easily gather, the Copernican arguments were much more solid. And perhaps worst of all, since those arguments were, in fact, written in Italian rather than Latin, common Italians could readily understand them. And as far as the Church was concerned, Galileo made a few more errors of judgment. His fictional defender of Aristotle, who spouted the same arguments the Pope had been making, happened to be named Simplicio, the simpleton. And perhaps most damning of all, Galileo's new book challenged the Church at the very time when it was being challenged from all sides. Galileo was put on trial in 1634. His fame and prestige made it unthinkable to go further than the mere threat of torture. But to Galileo, who knew very well how machines worked, that was enough. He publicly recanted the Copernican system of planetary motion. Ironically, in the future, no serious scientist would deny Galileo's evidence. The principle of inertia, conceived by Galileo and refined by Descartes, became Isaac Newton's first law of mechanics. As far as the Church was concerned, Galileo's name would eventually be vindicated, but it would take a very long time. As recently as 1983, the Galileo controversy was still unresolved. In that year, Pope John Paul II asked that the dispute between Galileo and the Church finally be put to rest. He said, "We cast our minds back to an age when there had developed between science and faith grave incomprehension, the result of misunderstandings or errors, which only humble and patient re-examination succeeded in gradually dispelling. The Church herself learns by experience and reflection, and she now understands better the meaning that must be given to freedom of research." But at the time, even for a famous scientist with an unpardonable ego, public humiliation was not considered punishment enough. Found guilty, in spite of his famous retraction, Galileo spent the remaining 8 years of his life under house arrest at his estate near Florence. According to legend, as Galileo headed into the exile of house arrest, he said, "Eppure si muove." Nonetheless, the earth moves.
Galileo made his real reputation by means of his great discoveries with the telescope. Before that, he had been known only to a handful of experts, but afterwards, he was famous throughout Europe. As a faithful son of the Church, he knew it was making a terrible mistake in turning its back on Copernicus. But the Church, under pressure from the Reformation, hardened its position on the literal interpretation of the Scriptures. Galileo was naive and arrogant, and he thought he could make the Church change its mind by means of logical, scientific arguments. That might have worked earlier, when the Church was more intellectually flexible, but in the 17th century, it was hopeless. Furthermore, Galileo did something that was even worse. Instead of writing his book in Latin, which only a handful of scholars would have understood, he wrote it in Italian, which anybody could understand. That was a challenge the Church couldn't ignore. And so, in 1634, he was put on trial. And in spite of recanting publicly his Copernican views, he was made to spend the last 8 years of his life under house arrest at his estate at Arcetri, near Florence. When he died, his body was buried in a cathedral, and it's still there, in the Church of the Holy Cross in Florence. That is, most of his body was buried there. I like to think that Galileo was defiant to the very end, and one of his fingers can be found on display in the Museum of the History of Science. I'll see you next time.
Hidden within the law of inertia is the fact that all motion is relative. Whether a body is in motion or at rest depends strictly on the point of view of the observer.